Alright, so we are talking about a fluidized bed cold feeder pressure PID controller. This is our project. We have a system here, and it's got a couple inlets of a fixed volumetric flow rate, an outlet of a fixed volumetric flow rate, and then it's got a control valve with a PID loop that is hooked up to it. Our goal is to maintain a certain pressure inside the system, and the control valve current PID loop does not do a very good job of maintaining that pressure. So our goal is to maintain and improve the PID controller in place. So here's a physical picture of our system with a couple our inlets and our outlet, and then our control valve is right here. And there you go.
So we made an energy balance to model our system, and we just did an accumulation of moles in the system with our moles coming in and moles coming out. And here we have our constant volumetric flow rate, and that has its pressure coming in. We also have constant volumetric flow rate coming out from the top with the system pressure, and then the volumetric flow rate of the valve. And here we have the equation of what the volumetric flow rate of the valve would be. It's dependent upon the valve coefficient and the lift, while this valve is linear, so it's just L, and then the pressure drop across the valve with the specific gravity of the fluid inside.
So with our energy balance, we modeled a step test. You can see that over here. We brought it up to 300 psi. Once we got there, we opened our valve 50%. This is our output, this is the input. This is the model of what happened to the pressure as we did that. Our gain, Kp here, is our delta Y, our output, over our delta U input, which gave us a value of negative 2.7 psi percent valve. Our tau P at 63% of the way to the set point, where how long did that take? It was 30 seconds, and our dead time was 0 here.
So another method we did was to linearize the energy balance, and what we did was make the energy balance fit the FOPDT equation. And we did that over here. We have alpha and beta, which are two constants, and from the FOPDT model we have alpha equals 1 over the time constant, and we have beta, which is the gain over the time constant. And over here are our values. Our gain was negative 7.8 psi per percent valve, and our time constant was about 28. And once again, we had no time delay on this method.
So the next thing we did was we got actual data from the system, and we let the system get to about 300 psi, and then opened the valve and took that data. We tried to use an optimizer to fit the data to an FOPDT model. We got a positive gain of 6.8, time constant of 1.9, and a negative time delay. And we know that this isn't really possible. We know we need a negative gain for our system, and that we can't have a negative time constant or a time delay. So we are guessing that it's probably an error in our instrumentation, and we'll need to do more with that.
Awesome. So looking at a comparison of all three models, we've got our first principles model in blue, linearization model in green, and the FOPDT model in the red with the process data in black. It's pretty clear looking at this graph that the linearization method is the best fit. So that is the model that we're going to use going forward into our PID controller. So with our PID controller, because our dead time was 0, we use simple PID tuning parameters to get our initial PID parameters. So we got a Kc of negative 0.128 psi percent valve, a tau I of 28.619, and a derivative term of 0. Looking at what the result, it looks like our gain was pretty aggressive because we have a lot of oscillation every time we get to the set point. And if you look at the valve, it's opening and closing from 0 to 100% really rapidly. That's not ideal because it's going to wear out a system, and it probably is not even practical in reality.
So when we tuned our PID controller, we had a more conservative gain, as we see here, and that caused very little oscillation, and it also caused the valve opening not to be like the other one, where it opened all the way and closed very rapidly. And we could also see that our overshoot is very small, as well as our decay ratio, so we know that this is a pretty well tuned controller.
So currently the system has been taken down, and so in the future we plan to, when it's rebuilt, to implement our controller parameters to the coal feeder, and we are confident that it will improve the controller. And that's our presentation.
Thank you.
Amen.